So in our previous lecture, we discussed on the calculation of design bending moment capacity or the nominal moment of resistance of a singly reinforced rectangular beam. Today we will look at the concept of balanced under reinforced and over reinforced section. So if you are given any rectangular beam section to analyze and you have to find its moment of resistance, you will be given with its cross-sectional dimensions, which includes the effective depth or the total depth, the width of the beam, the grade of your concrete, and the value of your steel reinforcement bars. So before determining the moment of resistance, you have to know whether your section is balanced, under reinforced or over reinforced. Then only you can calculate the moment of resistance. So let's look at this concept here. The moment capacity of an under reinforced beam is controlled by the steel, whereas for an over reinforced beam it is controlled by the concrete. We have already discussed about this several times. The value of x by d. X means the distance from the topmost compression fiber or the extreme compression fiber to the neutral axis. That is, this is the neutral axis depth, and d is the value of the effective depth of your rectangular beam. So the value of x by d of a singly reinforced concrete beam is not allowed to exceed the limiting values, xu by d. So xu is the depth of the neutral axis at ultimate stage. So this value of x by d has some limiting values, and these limiting values should not be exceeded for your rectangular beam. So limiting values are given here. We will see in next slide how we calculate these limiting values. So if we have used mild steel, that means steel with Fy 250 Newton per mm square, the limiting value of xu by d is 0.531. For high yield strength bars, for 415 grade steel it is 0.479, and for 500 grade bars it is 0.456. So let's look at the diagram to understand the concept of balance section here. If you look at this bold line here, this represents the strain profile of a balance section. So the compressive strain in concrete is always equal to this value of failure strain, that is 0.0035 is given in our code IS 456. Remember, this limiting value of compressive strain may be different according to the different code of practice. For example, if you are using the American code ACI 318, then the value of this limiting strain in concrete is given as 0.003. So for IS code it is 0.0035. And similarly, for this balance section, you can see that the strain in your steel is equal to the yield strain, that is epsilon y divided by 1.15, which is equal to 0.87 Fy. 0.87 epsilon y. So this is the case of balance section. Now if you look at the over reinforced case, you can see that the over reinforced case is represented by this diagram here. This green line here represents the strain diagram for over reinforced case. For over reinforced case, the compressive strain in concrete is the same, whereas now the strain in our steel is less than the value of this yield strain. So in this case, the concrete reaches its failure first before there is any steel yielding. Hence, it accounts for the brittle failure of our rectangular section. And finally, if you look at the case of under reinforced section, this blue line here represents your under reinforced strain diagram, and in this case the strain in concrete is greater than the value of epsilon y divided by 1.15 plus 0.002. So you can see that if this is the depth for balance condition, for under reinforced case, the depth of the neutral axis is reduced, whereas for over reinforced case, the depth of the neutral axis is increased. So to ensure that this over reinforced condition does not exist in your beam section, we have to have some limiting values of this neutral axis depth. And instead of neutral axis depth alone, we will take the ratio of neutral axis depth to the effective depth of our beam, and these limiting values are not to be exceeded to ensure ductile failure in our rectangular section. So how do we get these values of limiting values of xu by d? We will look now. So now let's look at the depth of neutral axis. Beams are assumed to fail when the failure compression strain is reached in concrete. The steel need not reach yield stress at the same time unless it has been specifically designed to fulfill this condition. So equilibrium of forces is required at all times, hence we will compare these tensile forces and compressive forces. So tensile force is represented by the stress in concrete multiplied by the amount of steel reinforcement. FST is the stress in our steel bars, and the compressive forces is represented by 0.36 FCK-BX. We looked at the derivation of these compressive forces in our previous lecture, where we added the magnitude of the forces due to this rectangular stress block and due to this parabolic stress block. The total force came out to be 0.36 FCK-BX. From this, the value of X, which is the depth of neutral axis, is given by FST into AST over 0.36 FCK-B. So what is the value of FST here? If we assume that our beams are under reinforced, the yield stress of 0.87 Fy is reached first in steel reinforcement. So we will substitute the value of 0.87 Fy in place of FST, and then we will divide both sides of this equation by d, that is effective depth. If you do this, you will get the following equation xu by d, which is given as 0.87 Fy AST over this value. So now the x has been changed to xu because xu is the depth of the neutral axis at ultimate failure of under reinforced beam. So we have supposed that our steel has yielded, hence ultimate failure of our beam section has occurred. Thus the x has been changed to xu. Here this u represents the depth at the ultimate state. And this value of xu by 2 you can find in NXG of your IS code. If you want to know, or if you wish to know how this equation was derived, now we have seen it, xu by d. Okay, what is the limiting values of xu by d? Here we derived the formula for xu by d. Now we will determine its limiting value. So in order to avoid brittle failure, the steel strain epsilon SU at failure should not be less than this value here. This formula or this condition we got from our assumptions of flexural analysis. The last assumption, where we discussed that to ensure that brittle failure does not occur in our concrete, the steel strain should be at least this minimum value. So we have the strain diagram here. Use the property of similar triangles, then we will get the strain in concrete over the strain in steel is given by, if this is the value of xu and this is the value of epsilon cu, then this is epsilon su over d minus xu. Now rearranging this equation, you will get the value of xu as here. Now substitute the value of epsilon cu as 0.0035 and epsilon su as this, as we got from here. Use the formula or use the value of the modulus of elasticity of steel as 2 into 10 to the power 5 Newton per mm square. Then you will get the value of xu by d limiting, which comes out to be 805 over 1265 plus Fy. Let us say this is Ku. Now, for different grade of steel, you can put this value of Fy and then you can get the limiting value of Xu by d. For example, in our table, in our previous slide, we looked at the limiting value of 250 grade, 415 grade and 500 grade. Substitute these values one by one and then get the value of Xu by d limiting for each Fy. Now let's continue. The lever arm distance is represented by Z, and let us say that it is represented as JD, where J is the ratio of the lever arm distance coefficient. We will see here what is the value of J. So the lever arm distance is D minus Xc. Xc means, as we saw in our previous lecture, if this is our force diagram, here the tensile force is acting and here the compressive force is acting. The line of action of this compressive force is at a distance of Xc from the extreme compression fiber. Then the distance between the line of action of C and T is our lever arm. So it is, if this is our total effective depth, then our lever arm is equal to D minus Xc. Xc value we derived as 0.416 Xu, and if you take D common from these two terms here, we will get D into this formula 1 minus 0.416 Xu by D. Now we have represented the formula of our lever arm in terms of Xu by D. So this whole equation in these big brackets, you can say this is the value of J here. Similarly, we will try to express our limiting value of concrete compression in terms of Xu by D. So our formula for the compressive force was 0.36 Fck into Bx. Now this, in terms of Xu by D, if you multiply by D here, then you can write it as Xu by D. So this formula we have written here. Now represent this value 0.36 and Xu by D as K1. Then our formula for the limiting value of concrete compression is given by K1 Fck Bd. Similarly, we will express our moment strength of the beam in terms of concrete compressive strength at C into Z. Here we derive the compressive force. Now the concrete compressive strength will be this value of C into lever arm. So 0.36 Fck Bxu into this is our lever arm. Now we know that if you take this D minus 0.416 Xu is represented as J here. So this becomes JD and then Xu by D. Instead of this Xu only, we have first divided by D and then multiplied it by D. So we get this formula here. Now represent 0.36 Xu by D into J as K2. Then this becomes K2 Fck Bd square. So this is moment resistance in terms of compressive strength. If you want to express it in terms of the tensile strength of steel, then Mn or the nominal moment resistance becomes Tz, where T is represented as Fst, Ast and Z is the same here. This is for all values of Xu. But if the value of our Xu is less than the limiting value of Xu, then this stress in steel can be assumed as 0.87 Fy. So this is the value of Mn in terms of tensile strength. Now we can see here, this first three rows are the same as we had in our previous slide. You got this value of Xu by D limiting from our previous formula here by using this equation. Now once you get the value of Xu by D limiting, you can put this value in the equation for J. So J we have 1 minus 0.416 xu by d. Put the value of xu by d, then you will get the limiting value of J for all these three grades of steel. And then after determining J, you can determine K1 and K2. K1 means 0.36 xu by d. Put the values of xu by d for each grade of steel and get the value of K1. And similarly for K2, put the value of xu by d from this column and J from this column. Then you will get the limiting values of K2. So all of these are limiting values, and all of these J, K1, K2 are derived from the limiting value xu by d. So you can remember this also for your own purpose. 0.531 for 250 grade steel, 0.479 for 415 grade steel, and 0.456 for 500 grade steel. So this is how you determine the limiting values of xu by d and ensure your section is under reinforced. So one final topic to discuss before going to the design of singly reinforced rectangular beam is the resisting moment strength for balanced section. In this current section and in our previous lectures, we are discussing the analysis. We are given with the cross-sectional dimensions, steel reinforcement, concrete gate, and we are looking at how to calculate the value of moment of resistance Mn. So before going into the design, we will see one final topic left to discuss is the resisting moment strength for balanced section, which we will see in our next lecture. So till then, stay safe and we'll see you soon. Thank you.